Welcome to the ChemDoctor, and what I'd like to do in this series of presentations is describe the concept of photoelectron spectroscopy. This is a technique that is now used to analyze the atomic structure of elements and molecules. In terms of learning chemistry, photoelectron spectroscopy, or PES, is going to be important if you're taking advanced placement chemistry, because it's one of the new things that they've introduced into the curriculum. If you're taking a general chem class at the university level, on the other hand, whether or not your professor delves into PES is going to depend on whether or not that particular professor is an atomic structure jockey or not. And those courses, generally speaking, depend a lot on the specialty of the professor, whether or not they get into detail like this. Regardless, if you're visiting this video because you want to learn about PES, there's a couple of things you need to make sure that you understand before you delve into the presentation. The first is you've got to be comfortable being able to determine electron configuration and understand how it works. And secondly, you need to understand orbital diagrams, because I'm not going to have time to go into the detail on those particular concepts here. Rather, I need to be able to rely on the viewer's basic understanding of that. For my model that we're going to focus on here, I'm going to utilize neon, which has a total of 10 electrons and an electron configuration which is shown here. Now, what is the importance of this particular technique? So photoelectron spectroscopy, or PES as the acronym is known, it's a technique that allows us for the first time to analyze the nuances behind electron configuration. And before I get into the details about this, it's important that the viewer understand, when they look at an electron configuration, exactly what this means. So I want to draw your attention over here to the right for a minute, and let's discuss the electron configuration of neon. You need to understand that the way the configuration works is that there is an implication for the energy of the electrons that appear in the different energy levels of the structure itself. So on the right, what I've done is converted the electron configuration of neon into the orbital diagram that has been arranged in terms of a number of different factors. The potential energy of the electrons, the ionization energy relationship, and force of attraction. So let's take a couple of minutes to look at what I mean by this. First off, it's important for the viewer to understand that the energy of an electron is proportional to the product of the charges between the protonic charge that's in the nucleus and the charge that's on the electron, that I can represent this way, okay, divided by the distance that those two, or that those charges are separated by. So there's a relationship between the distance that the electrons are from where the protonic charge is. So in my diagram here, I'm showing the protonic charge located here, and my charge, which I just am indicating by a singular charge of plus. It doesn't imply that we're dealing here with +1. What you want to realize is that this is a generic diagram, and whatever element that we're dealing with, you would then insert whatever the protonic charge is. So in the case of neon, we're dealing with a total of plus 10 protons. And so I'll just jot that in here to emphasize that fact. All right, now, energy level 1 is the energy level that is closest to the protons. And so, in essence, this is got the lowest potential energy. These electrons have the lowest potential energy of any of the other electrons that are in the electronic structure of neon. I'm going to draw a circle around these two electrons because they represent what we call core electrons. And the core electrons are the electrons that are closest to the proton and separate the protonic charge from what we call the valence electrons, right? And the valence electrons, I'll put a box around these guys, are the electrons that are found in the outermost energy level of the atom. All right, outermost energy level of the atom. And the valence electrons are always separated by core electrons. All right, now, so if we come back to my diagram then, I will indicate, so these guys here, therefore, are my valence, and I'll just abbreviate that this way. Now you can see from my diagram, and I would suggest that the viewer actually gets used to drawing a diagram like this on a piece of paper. If you want to truly understand this, you should be able to do this from memory and be able to apply, like I am here, the basic structure of any particular element. I do want to emphasize that the way I've drawn this diagram is true for elements between 1 and 20. So from hydrogen to calcium, we will learn in subsequent presentations that the energy arrangement of these orbitals is going to fluctuate a little bit when we get out here beyond or to the point where we introduce the 3D elements or the 3D suborbitals. All right, and for these initial presentations, we're only going to focus on the elements that actually rigorously follow the electron configuration as you've most likely learned it in your classes. But coming back to the matter at hand, if we look at the valence or the electron structure of neon, the 1s electrons are the core electrons. They are closer to the protons than the valence electrons. You can see that there's a number of concept factors that are important for you to understand. The first is these 1s electrons are lower in potential energy than the valence. If I come up here to my valence and I draw a line over, you can see that where we hit into my potential energy arrow, it's at a higher location than the 1s. The 2p electrons are slightly higher in potential energy than the 2s electrons. Similarly, if I bring my arrow over for my 1s, you can see that to remove the 1s electrons, it should require more ionization energy than to remove a 2s electron versus a 2p electron. So the 2p electrons you would expect in neon should be easier to remove, a lower ionization energy than the 2s electrons, and the 1s electrons should require more energy or higher ionization energy than either the 2s or the 2p. Similarly, it will require an exertion of more force to remove an electron from the 1s than it will from a 2s or the 2p. That's what this electron configuration implies when you write it. All right, and that's why before we get into the PES, it's important for the viewer to understand that when you write an electron configuration, all of the things that I just talked about here are implied in this configuration. Now, how does PES work? So the PES is essentially a box. It's an instrument in which we can introduce a sample of a particular element. That sample can be gas, it can be in a liquid form, or it can be in a solid form. Now, the way the PES instrument works is that it directs a beam of light onto that sample. Remember that you can consider light to be a stream of particles. And I have to assume that you've had some basics in atomic structure here. Remember that light has both a wave and particle characteristics. The energy of these particles, and we call these particles, they have a name, we call them photons, all right? A photon we can look at as being a subatomic particle. We can look at it that way. Another way to look at this is that it would be like a subatomic bullet. And I like using the analogy of bullets because most mortals have a concept of a bullet, right? So you can think of a light wave of being a stream of subatomic bullets, and the energy of these bullets, it will equal the product or the multiplication of two constants divided by the wavelength. All right, so this is the wavelength of the light wave, and these two factors here are literally, it's just the product of two constants. It's the Planck's constant times the speed of light. And I don't want to complicate my presentation by going off onto a tangent about this. What you guys need to realize is that this is simply a constant. So we can boil down this discussion into the following thing. Light is a stream of particles. Those particles, each particle has a certain energy, which is proportional to a constant over the wavelength of the light. So saying this another way, the energy of these particles is proportional to 1 over the wavelength. Now, how does this relate to the PES instrument, and how does it relate to analyzing an electronic structure? So the PES instrument is capable of beaming a stream of particles onto an atomic sample. All right, so if we were to introduce neon into a PES instrument and then shoot a stream of photons into this collection of gas particles, which is all made of neon, how can we use that maneuver to understand the electronic structure of this element? All right, so what you need to understand about this particular instrument is that it knows intimately what the energy of the photons are that are being introduced into the sample. And the energy of these photons is going to be equal to the ionization energy of the electron plus kinetic energy. All right, that was a mouthful. What do I mean by this? All right, so Einstein learned a long time ago when he introduced the concept of the photoelectric effect, that you can take a beam of light and literally direct it onto some kind of a sample of material, and you can cause electrons to be ejected from that sample. What he learned is that certain elements have a certain relationship to energy. In other words, only certain wavelengths will eject electrons from certain substances. So the PES instrument focuses on that concept. In other words, we can take a certain wavelength of light that the PES instrument knows intimately, project it onto a sample, and cause electrons to be removed. Now, the instrument itself knows two things. It knows precisely the energy that's being emitted onto or being directed onto the sample, and it can determine the kinetic energy directly of the electron that it causes to be ejected from that sample. So we get two pieces of information from the PES then. We're going to know number one, precisely the kinetic energy of the escaping electron that's being made to escape by the energy of the light wave that's being directed onto the sample. And the second thing that we're going to get from it is we're going to get to know how many electrons escaped that had this exact kinetic energy. Now you can see when you look at this, we can therefore know the ionization energy of that particular electron and how many of those electrons had that ionization energy by utilizing a computer to literally take the difference here. So the ionization of that electron, or those electrons, because remember we get to know how many have a certain kinetic energy, and that ionization of those electrons is going to be equal to the energy of the photon. So in other words, the energy of the particles that were directed onto that sample minus the kinetic energy. So from a PES experiment, we're going to know the ionization energy of those electrons, and we're going to know the ionization energy of the total number of electrons that are ejected from each of those samples. So now, coming back over here to my diagram, what do we get to know then? So if you look at how this is set up, the potential energy of a particular electron is equal to the same in magnitude but opposite in sign of its ionization energy. So the energy to remove an electron is this value here, where I'm drawing this green arrow going up. So to remove one of these 1s electrons from neon, that maneuver is going to require the introduction of this much ionization energy to remove that electron. The PES instrument can do that because we can project exactly a known amount of energy onto the sample. We can collect exactly the amount of kinetic energy of the leaving electron. The computer takes the difference between the energy that's projected onto the sample, the kinetic energy of the electrons that are removed, which gives us the ionization energy exactly of that particle. And therefore, we can know or analyze the electronic structure of the individual electrons that are in this sample. So what kind of information do we get from this? So shown here would be the collected information from neon put on a PES scan. Now when you look at this, here's how those scans are going to look. So we're going to have ionization increasing from left to right on the horizontal axis here. The 0 mark I've put out here is arbitrary. This is where the electron is removed entirely from the atom. All right, and as we move towards this part of my axis over here, at this point, the ionization energy is increasing. The vertical axis tells us the number of electrons that has the corresponding ionization energies determined by the PES scanner itself, by the instrument. And you can see for neon now we get a series of peaks. The interesting thing is that we're going to get a total of 3 peaks. The first peak that we get here with the highest ionization energy, the energy that is closest to the left part of our axis here, this peak proportionately has 2 electrons in it. And then as we move to the right, you see that we end up encountering 2 more peaks. The first peak we come to, again, is shorter than the second one to the right. It has the same size as the first peak that we see here to the left. So proportionately, it has the same number of electrons in it. Turns out, has 2 electrons. The last peak we have here, the one furthest to the right, which has the lowest ionization energy compared to the inner 2 peaks here, proportionately has a total of 6 electrons in it. So you can see that these peaks and their shapes proportionately match the electron configuration that the quantum mechanical model has proposed for the electron configuration that we're utilizing for the elements as we extend from 1 to 20. All right, now I emphasize from 1 to 20 again because once we get past calcium, we're going to see that there are going to be some changes in how we have to think about the electron configuration of period 4 elements. But what I wanted to do in this particular presentation was open the door to understanding how the PES works. And in the next presentation, what we're going to do is practice looking at some scans of elements that are between 1 and 20. Now, what I'd like to do is go ahead and close this video. I'd like to thank the viewer for watching ChemDoctor. You can find additional videos in this area of atomic structure located at my website, which is www.chemdoctor.org. Again, thanks for watching, and I'll see you in the next video.